Hello everyone, welcome back to ECE410 Power Electronics. This is class number 4. Today we're going to talk about switching matrix, circuit laws, and switching devices. So let's start with the whole thing here. What is a complex system for a converter? So if you have a converter, if you have a converter here, you have a converter in the middle, for example. Then you connect with load, then you supply from a source, right? So this converter needs hardware, also need software to operate it, and also interface for these two sides here. These two sides needs interface. That's why you need hardware, software, interface to make the converter a complete design. And device you use in converter, it depends on what the power rating you're handling. It can go from nano amps of current and to thousands of current. Like this over here, they can basically carry hundreds of amps. And like your Apple device, inside this, they use very, very small current, like nano amps of current. And we have other devices in between them. So depending on what his application is, your converter could be designed with a device that very small rating for the voltage and current, or could be designed with a very high rating for voltage and current. So in converter design, there could be DC-DC converter right here. So both sides are DC, or could be AC-AC, or in between, right? So for DC-DC, you're basically changing the voltage level and the current level, right? For AC-AC, you're doing voltage, current, as well as the frequency. So you're doing voltage, current, and also frequency, right? So that's the difference between AC-AC and DC-DC. If you look at this one over here, this is a electric car vehicle arrangement. So this is when you connect to the grid, when you bring home or your garage, then you connect to the grid, and grid supplies AC. So AC becomes DC here with the rectifier. Then your charge controller controls how much current goes through this to connect you charge your battery over here. So during that time, when you're charging, your energy going following this way here, and this motor is basically acts as an inductor. So motor is not running, it's basically acting as an inductor during the charging process. And I will ask you in the class, what is the purpose for this diode here? So think about it. What is the purpose for the diode? All right, think about it. So during the charging process, your charge controller controls the energy flow from the grid to the battery. And over here, so let's say if you this is on, this is on, this is on, so your current flowing from here and coming back and going to the neutral. All right, so that's how your energy flow works during the charging process. All right. Now, if you just think for the switching analysis, we don't think about all those control circuit or peripheral circuit. We only think about the switches. So all the switches are now here. There are 5 diodes here, right? And you have 6 transistors there. So there are 11 switches for the just to analyze the switching circuit. That's how it works. We don't care about all other peripheral circuit when considering only the switching action of the converter. And another one here, another example here, if you're doing a panel backlight for LEDs, and look at that, this circuit has all the control circuit inside it. But if you now only concentrate on switching, I have only 2 switches over here, one here and one here. I have only 2 switches, that's right here, one here, one here. So only thinking about the switching action, not all other control device. So what is the control device here? You have a gate driver to drive the MOSFET, and before that you have a PWM controller to control how long it's going to turn on and off. So gate driver, PWM controller. Then you also need the reference voltage and ramp to make the PWM signals. That's all here, but for the analysis of the switching circuit, only need the switches. So if you look at over here, for a for that particular one, we have two switches, so there will be four different combinations, right? One on, two off, one off, two on, both off. So there are four different combinations. So that is basically comes with the two switches. 2 to the power 2 will give you 4, right? So that's how combination you get from the switching actions. And if we go to the next one here, they have 11 switches. You can think about they have 11 switches. So the 2 to the power 11 switches will give you 2048 combinations, right? 2048 combinations. So it's too many combinations to think about it, but before we analyze each of the combination, we have to make sure that what combination is really useful, what combinations are not useful. Then we can only analyze the useful one. All right, that's the goal for analysis of the switching actions. To do that, we have to make a like there are m inputs here and n outputs here. There's a m times n switching here. So to analyze those, we can make them mark at 1 1 1 2 as a row and column. Then we can put to the Q1 1 Q1 2 and so on. So when one Q is on, 1 is on, when is 0 is off. So it at any given time is either 1 or 0. So from there you can have a relation between input and output voltage, input and output current with the Q matrix. The Q matrix is right here. So that matrix, which one is on, which one is off, that is controlled by the control circuit and software. That will give you the relation between voltage, output voltage and output current to an input voltage, input current. That's what you want. You want to control your output voltage, output current based on the switching action. So this action will be controlled by your control circuit. Right? So now, before we go there, I have to understand two laws we have learned long back is KVL and KCL. KVL basically says that if you try to understand the KVL basically says in converter circuit is that you cannot connect two dissimilar voltage source in parallel. That's the law here. So when you connecting two sources together, there should be the same sources when it connect them in parallel. So there's a law here. Never ever attempt to violate the KVL law, and KVL violation produce high current. That high current can destroy everything in its way. So remember that KVL violation creates the high current. So KVL violation all right, so never ever try to violate the KVL law. So why is it high current? Let's see here, if you have a voltage over here, source, let's say 5 volts only, then you connect it with another voltage source over here, 3 volts. What will happen now? There will be circulating current here, right? So that there's nothing here, it's a wire. So any amount of current goes here, it will be voltage difference between them is 2 volts over 0 ohms, right? So that can go ISC short circuit could go theoretically infinite, right? So that would not be infinite because your internal resistance of the batteries or sources will limit that, but still they will be very high. That could basically put this one on fire, right? So that's why I say never ever try to violate KVL. KVL violation produce high current. And again, this is also KVL violation here. You have a 20 volts here. There's nothing here. So 0 volts over here, right? So you're connecting to different dissimilar sources that will produce really high current. So again, produce short circuit current, which is very high. All right. And next one is KCL. KCL violation is that KCL says that you need a path for the current. The current needs a complete path. If you don't have a complete path, then current, if it will take an unusual path. That means KCL violation will create a high energy, which is a high potential. So KCL violation produces high potential. So KCL violation is not as critical as the KVL violation. KCL violation, if you don't have a complete path for the current, if the current is not strong enough to find the unusual path, it's going to stay there because most of the time current cannot go through the open circuit, right? So that is not always dangerous as KVL. But over here you can see that there's a two open node here. So the current was too high that they can find a path through the air, which is basically sparking. So you're breaking the barrier of the air. That could happen if you have the high amount of current in there, or high amount of potential generated by the current to break the path for in insulator. So one of the example for KCL violation is that if you have a inductor, right? It is inductor, you know that you cannot change the current through the inductor immediately. It cannot be done instantaneously. So current would be going the same direction, right? When switch is open, which is open here, current is still pumping through the inductor. That can produce a very high voltage over here. So VL would be L di dt. L is let's put the number here at 10 millihenry, so 0.01 Henry, right? And di dt, so 10 amps over 1 microsecond. So 10 amps over 1 microsecond is 10 to the negative 6, right? If I do that math, it would be 100,000 volts. So this 100,000 volts over here is to be huge voltage for this small gap. If the gap is so small, that could break the gap and the current, the charges can escape through the open air. That could be dangerous because that will produce spark and could potentially catch in fire. All right. So if your inductor inductor is high, that could limit the change, also limit the voltage. So right here, that could be a potential over here that the circuit in the converter circuit, these two switches always complementary, right? There's none of them on and off, so that we do it very quickly. That energy, even though we're trying to violate the KVL or KCL, but we don't do it for long enough to destroy the circuit. So KCL generate extreme voltage, right? As current tries to maintain its flow. Explain is basically, I just give you the equation here. VL is L di dt. Let's try to if we maintain the current change very rapidly, you have an inductor that could produce a very high voltage. So that again, if you do this over here, is sometimes you when you're generating high voltage here, fuse doesn't work, right? There's no fuses, that's why it's generating high voltage. So fuse doesn't work against the voltage. So fuses does not work against voltage, right? KVL violation are KVL violation, you can avoid them because KVL violation generates current, so you can use the fuse to avoid them. KCL violation, you cannot if KCL violation, if you have a long time there, it produces high potentials that could produce spark. So if the fuse doesn't work against KCL violation, so fuse doesn't work. That's why it's not easy to That's why it's not easy to protect against the KCL violation. Over here, if you have an inductor connected through a voltage source for a long time, that will violate your KVL actually, because this becomes short circuit after a long time. So that is basically violating KCL. And same thing with the capacitor. If you have a capacitor, you pump the current constantly, that will produce that will go over the capacity of the capacitor, could destroy it. So that also not a good thing for capacitor. That will find a path for the current here, that will be the KCL violation. All right. So again, a constant voltage across the inductor is a bad thing, because inductor becomes short circuit, and a constant current through the capacitor is a bad thing too, because the constant pumping of charges will exceed the capacity of the capacitor. That will also produce a current spike, charge spike through the capacitor gap. For the source emulation, this is the constant. There's nothing called constant current source, but if you have a large inductor across a voltage source, and if it's not constant voltage source, it will be it is subject to switching. That could be temporary things as a constant current source. And if you have a big capacitor across a current source over here, again it's not a constant current, is all subject to switching. That could be act as a constant voltage source. So remember that energy storage, we talked about that. Voltage across an inductor over a period is always zero, and current through a capacitor over a period, average current is always zero. So we're going to ask this question to you in the class to make sure that you understand them. And also I'll ask this in the class too. Let me know what you think about it, okay? That's all of for this lecture over here. I'll see you for lecture 5.